right, so as we said, word sense disambiguation is this task where we try to define what sense is a certain word meant to belong to given the context in which it occurred. All right, so why do we want to do this? Because, if you're doing machine translation or question answering, etc., as we said before, this is very useful. For example, for machine translation, there could be different possible translations for a word from English to Spanish, let's say. So you want to know which one we're talking about here, right? You remember probably the example of avocado in French, but you could come up yourself with other examples, I guess. Speech synthesis, which is the task of taking text and producing the audio. So it's like, reading text. It has to know which sense a certain word is meant in a sentence, because there are specific words like breed, bread, and base, bass that your speech synthesis will be erroneous if you didn't know what sense we're talking about. All right. So there are two types of word sense disambiguation tasks. There are two types of WST tasks. So there is the lexical sample task and there is the all words task. So in the first one, there are specific words that we're going to mark. So these are target words, and there is an inventory of senses for each word. So your task would be to, there are multiple possible senses, and you need to choose the one that is appropriate. All of the other words are kind of ignored. You only have to worry about the ones that are marked as target. The all words task, which you could infer from the name. So every word in the text is, something we need to disambiguate. So, or we need to assign a sense to. Okay, so this is something like POS tagging, where we had to give a POS tag to each word, but this time we have to assign a sense set from WordNet to each word in the text. Okay, so there are three approaches or three machine learning methods in which that we can use for this: supervised, dictionary, and semi-supervised. And we're going to see each one of them a little bit more in detail. So in the supervised one, you train a classifier, just like every time, in every supervised scenario. And this would require, of course, that you have some hand-labeled training data, so you can use to train your model and to test with. All right. In this case, what does your training data look like? Well, you have a target word, you have a context, and then you have a sense, and then you would have a human being who would tell you what is the appropriate sense set from WordNet in this specific case, so you can map it to. In the dictionary methods, there is no training data. So instead you use a sense dictionary like WordNet, and you would explore the sense relations, and we will see that is the LISC approach that does something a little bit different. Okay. And then you have the semi-supervised learning, in which you ask yourself, well, given that I have a small hand annotated data, how can I generalize and do some bootstrapping? So, to kind of use this hand labeled data and have something that is stronger than fully unsupervised, probably weaker than fully supervised, but with much less data, much less manual work. So we're going to talk about each one of these separately. So starting with the supervised word sense disambiguation. So what you have is a sense inventory, right? So WordNet senses, for example, you could make your own lexicon, or you could choose one that is domain specific. For example, you could see that in the medical domain, they have UMLS. And UMLS is an ontology that is organized in a similar way than WordNet. And when I say similar, I mean there is the hierarchy, but there is also the meronymy relations that are horizontal, that talk about parts and other types of relations. So if you are interested in medical, you want to check UMLS. You have an annotated training corpus, which means that you have a corpus where you have target words and you have the senses, the correct senses for each of these words. And then you have a set of features that you extract from the training corpus, and you have a classifier that's going to exploit these features in order to map your word to one of the senses, hopefully the correct one. All right, so how would we go about this, right? So some of these corpora, so we said there is the lexical sample task and all word task. So some of these corpora are available. Here you have some details about them. Sensival is now called Semival. So this is the same workshop that changed name. It's a very famous workshop in the NLP community, research community, and they organize competitions. And I guess that in 2007 and in 2001 and 1998, they had a competition for word sense disambiguation. And you could see here the number of instances that they had. And probably if you go to the web page, you will see also what was the highest accuracy obtained. All right. So when we talk about feature definition, this goes back to 1955. So one of the questions that we asked when we said how are we going to go about this is how are we going to define our features? So let's read this text. It's really curious to read this text from 55. Somebody has been thinking about this already. And it goes like this. It says, if one examines the words in a book one at a time, okay, as though an opaque mask with a hole in it, one word wide, then it's obviously impossible to determine one at a time the meaning of the words, right? So you have this little hole where you can see only one word at a time. And when you see the word, you can't really tell what is the sense of this word because you can't see the context. That's what he's trying to say. But if one lengthens the slits in the opaque mask until one can see not only the central word in question, but also, say, n words on either side, then if n is large enough, one can unambiguously decide the meaning of the central word. So what he's trying to say is that I don't need to read the whole text. I am certain that there is n words. If I see n words before, n words after in the word that I am examining, then I can tell what is the sense of this word. And then he follows up and says, well, the practical question is, what minimum value of n will, at least in a tolerable fraction of cases, lead to the correct choice of the meaning for the central word, right? And this is what we're gonna use for our features. We're gonna say, here is the target word, and if I look up this target word in WordNet, I'm gonna find, for example, let's say 10 possible sense sets. Now I'm gonna examine the context, and I'm gonna examine n words before, n words after, and I'm going to train a classifier, and I'm going to try it for n equals 1, n equals 2, n equals 3, 4, 5, and I'm going to empirically decide which one gives me the best results. So if you do this exercise yourself, you have this word here, okay, BASS, which could be bass or it could be base. If you do the exercise that Mr. Weaver said in the previous slide, but just by looking at the word itself, you can't tell what do they mean by it in this sentence. Do they mean bass, or do they mean bass, the fish, or do they mean bass, the guitar? So if we look at one word before, one word after, you say and BASS, watching, it probably becomes clearer, but not really, because you could be watching the fish, or it could be something else. But now you say guitar and bass watching YouTube, it becomes now obvious that we are talking about a music instrument, right? Okay, he learned how to play guitar and bass watching YouTube videos. So the approaches that we have for representing this context, now talking about it algorithmically, you can do this in 3 ways, all right? So the first way we can do this is using collocational features, which means that I'm going to take the position of each context word into account. So I don't care only about that this word appears in context, like for example, in the previous example, I don't care only about guitar being in the context of BASS. I also care whether it was the word before or 2 words before that or 3 words before that. The position is important. This is very different from this guy over here, where I only need to know what words appeared in the context. It's, you know, the typical difference between bag of words and collocational features. Then finally, I can use something that we learned in the previous lecture, lecture 12. I can use word embeddings. Okay, so let's talk about these a little bit. Let's start with bag of words. So if we take our previous example, I'm going to have, if I take my context as being -2 plus 2, so I take 2 words before and 2 words after my target word, I am going to build a vector. Obviously, the size of this vector is going to be the size of the vocabulary. And then I'm going to look up the words that are in context, like guitar and watching and YouTube and end, and I'm going to put 1 and the rest will be 0. So this will be my representation, and this is what I'm going to give to my classifier to choose what sense I'm talking about. If I choose to do collocational features, then assuming that I have a window of minus plus 2, what I'm going to do is I'm going to have to keep these guys in order, okay? So each one of these guys is going to be of the size of the vocabulary. This one is going to be the size of the vocabulary of the post tags, the tag sets, right? And this one is going to be, so this vector here, it is much bigger, or at least is 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4. So 4 times the size of the vocabulary plus 4 times the size of the vocabulary of post tags. So in comparison, your number of features is huge. And the bigger the size of the window, so if you decide to take this from plus minus 2 to plus minus 3, this is going to become much bigger. Okay, so this is something to take into consideration when you're choosing your features. At the same time, you have this collocational, you have this position that you don't have in the other one. And how do you decide whether you should go with this or not? Obviously, you have to do some experimentation and see which one gives you the best results. And you also have to look at latency, memory, and other practical things to make sure that the solution works for you. All right. So if you want to use like a feed-forward neural network, like the one we saw in lecture 11, well, you have your context words here. So this is 1, 2, the ones before, and then 1, 2 words after. And then you're going to do a feed-forward. The set of your classes is going to be the set of the senses. And actually, what you're going to get as an output, because this is a softmax, so remember that softmax gives you probabilities. So the sum of these probabilities will sum up to 1. And each one of them is going to be between 0 and 1. And what you want to pick the one that gives you the max, right? So the max probability. Okay. All right, so now for the dictionary-based methods, so that was the supervised ones. Then we'll talk about the dictionary-based, and finally we'll talk about the semi-supervised. So for the dictionary-based methods, it's a little bit of a different story. Why? Because we say we have no training data, okay? So instead, what we can use is separate dictionaries. So we have, like, for example, WordNet. And in order to obtain the candidate senses, what we're going to do is we're going to look up information that we have in our context. So we have that sentence that we are, we have the target word in the context, but we also have inside of WordNet, for each lexeme, we have some words, we have examples. That's what WordNet gives you. WordNet gives you a definition, but it also gives you examples of sentences in which this word is used in this specific sense. So what you could do in this very known algorithm called the simplified list algorithm is you can look at your sentence. For example, the bank can guarantee deposits will eventually cover future tuition costs because it invests in adjustable rate mortgage securities. And then you have 2 senses of the word bank here, in which one is talking about the bank for the river, and then you have the other one that is the financial entity, and you will see that there is an overlap here between your sentence and this one, and then you can kind of make a relationship and say, well, I guess that the target word here, bank, means more this specific sense. Okay? You might need some annotated data just to evaluate how good is the thing, but you don't need it to train anything, all right? Which makes a huge difference. Now, if you choose to use the LISC algorithm, and I think in homework 4, you will have to use the LISC algorithm. there are a couple of things to take into consideration. Is that many times the overlap of words that appear in your sentence and in the definition WordNet might be zero, right? So you can't tell really if there is any relationship between the sense in which the word appears in the context and that specific sense in WordNet. So what you want to do is you want to make sure that that overlap is better, right? So that your numbers make more sense. So there are different approaches to this. If you have a sense tagged example corpus, so you have some kind of tagged corpus, well, you can add examples from there. Okay, so this is one thing. So what you're trying to do is you're trying to augment your data so that hopefully when you have more text talking about that specific sense, your overlap will go higher. This is what you're trying to do. So if this doesn't work, what you can do is you can actually, now that you have the word, when you are in WordNet, you can choose hypernyms and meronyms, and you can grab their example sentences and see if there is some overlap. All right, so you have your sentence here. So this is your sentence. And in your sentence, you have blah, 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 bank, blah, 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 blah. And here is WordNet. WordNet has this structure, as we said before, with sometimes some meronym relations here and there. Now you look at bank and you look at these words that you have here, and let's say that bank is here and is here. And when you look at, for this specific sense set, what are the example sentences, and you look at this one and you look at the example sentences, maybe when you look, there is no overlap here. So there are no words that overlap here and there. So what you're going to do is we're going to go to the concept on top, the hypernyms, and you're going to choose the meronyms, and you're going to grab their example sentences and concatenate the whole thing and see if your overlap gets better. Okay. Another thing that you can do is that you can use embedded representation, so word embeddings, for each word in definition, and then you choose the sense, and you can now do a similarity kind of thing. So now you can compute a distance, because you can represent your sentence using the embeddings, represent the examples in WordNet using the embeddings, and then you can compute some kind of similarity, and hopefully that gives you a better way to evaluate which sense set is the closest. Okay. All right. The other question is, how do we evaluate word sense disambiguation? Ideally, what you want to do is you are doing word sense disambiguation, as we said in the beginning, because you want to feed it to some other task, some higher level task that's going to use that. For example, when we said machine translation or speech synthesis. So if your WSD is doing a better job, so let's say you have two systems, system WSD1 and WSD2, the better one is the one that makes the machine translation better. So you can see the impact in the higher level application. That would be an extrinsic evaluation. Okay. So another one for convenience, because you might want to evaluate your WSD separately before you plug it into the higher level application, is you can just do the accuracy, right? So for each word you define the sense and you see how many times, what is the percentage of correct sense tags, all right? But every time you're talking about any classification task, it is good to define some baselines, right? Because if you don't have a baseline, you don't know how hard is your task. You can have a very, very sophisticated algorithm that gets you an accuracy of 95%, let's say. And that makes you really happy. But then somebody can make something really basic and get 94%. So all of the intelligence, all of the sophistication, everything that you have done is only to get 1%. Maybe his approach or her approach is much simpler and is much faster, and you only lose 1%. So it's always good to have a baseline, something that is simple to compare anything that you have done to before you declare victory, before you say, well, my approach is the best. So a couple of baselines that work very well is that without using any kind of classifier, you could just actually pick the most frequent sense. So you go to your training data, and for each word, you see what are the senses that the human annotator said that are the correct ones. And then, for example, for the word bank, you're going to count how many times it was bank as a financial entity and how many times it was bank as a bench. And then you're going to take the most frequent one. And when you take the most frequent one, let's say it's a financial entity, when you go to your test case, to your test data, you're just going to assign a financial entity all the time. You're going to assign the most frequent tag all the time. And then you're going to compute your accuracy. So next time when you use a classifier, you should compare it to this baseline instead of nothing, or instead of comparing it to 50%, which is random or something like this. Okay. Another thing is that people usually use LESC as a baseline for elaborate approaches, right? So you're going to use neural nets and you're going to add a lot of things. LESC is a simple overlap of words in between your context and the WordNet example. So that's so simple enough to, that you can develop it in a few minutes, and it will give you a strong baseline to tell you how much is your algorithm adding, what is the added value of your algorithm. So if you want to talk about a little bit about what is the performance of this, what accuracies do we get? So it has been reported that accuracies of over 90%, we get them usually for the very, very, famous or popular examples. But then in Sensival 1, they made like a more fine-grained senses and a wider range of types. And the accuracy overall was around 75%, where people could disambiguate nouns 10% better than they could for verbs. So this gives you a little bit of an idea about where you should be. Of course, you should take these numbers and put them together with the numbers that we presented before for the data sets and say, how much human effort do I need in order to get here? How much manual annotation do I need in order to get here? And probably look at the LESC algorithm and say, well, here is LESC where I need 0 human annotation. How much do I get? All right, but baseline gives you the lower bound. The upper bound is to compare it to what humans are capable of doing. There is a way to evaluate how well can humans do, called the IAA, the Inter-Annotator Agreement. Inter-annotator agreement, simply when you're trying to annotate something manually, you don't want to do it with one annotator, because if that annotator has a bias or they didn't understand the task very well or something like that, then they're gonna create a data set that is useless. So you want to have ultimately 3, like an odd number of annotators, and then you want to see how much do they agree. Okay. The process is a little bit longer. Once you have done this, then maybe you want to choose, if you had 3 annotators, when you do the training, you want to choose only the items on which at least 2 have agreed, etc. But that's a different story. Now, but you can also use the inter-annotator agreement to evaluate how good is a human being. So if 2 humans can only agree on 75 to 80% of the times, that tells you how hard is the task. Because if it was simple, if it was something like POS tagging, they should agree at least like 98, 99% of the time. They would disagree only on very specific, very hard cases. So this tells you how hard is WSD. Now finally, for the semi-supervised word sense disambiguation, David Yarovsky, I think, if I'm not mistaken, this is GHU. He proposed a way to do bootstrapping and to generalize from a small hand-labeled dataset. All right. So David Yarovsky, he made 2 rules that are famous in NLP. One is called one sense, one tag per document or something like this. Where let's say that you are doing named entity recognition, and when you're doing named entity recognition, you have some text, and for each piece of text you say whether it is a person, or this is nothing, or this is a location, etc. Okay, and he said we're gonna make an assumption. Let's say one tag per document or per text or per something like this. Anyways, we don't care. But basically, if you see here Washington, D.C. being used because we're talking about the city, you can just consider that in this whole text, whenever Washington is being mentioned, we talk about Washington, the city. If there is another piece of text where we talk of Washington as administration, right, as the government, then you should just consider that in this whole document, whenever Washington is being used, we're talking about administration. So this is a rule to simplify things, but he's using it also to augment data, right? So if you are doing manual annotation or something like this, then you can just consider that every other Washington will get the same tag. All right, and here he's going to do the same thing. So he's going to say there is 1 cent per collocation, meaning when we have 2 words, whenever they appear with each other, my target word is going to always take the same cent set. So if I have the word BASS, okay, whenever it occurs with the word play, I am just going to say this means bass, okay, bass as bass guitar. Okay, and whenever I have the word fish occurring in a context with bass, then that means bass, which is a fish. All right. So what does that give me? If I have a small data set, so this is hand labeled, and I have here boom boom boom, and I see BASS, and it occurs with the word play. And my human annotator says, in this specific case, we're talking about the musical instrument. Let's say that I have a huge set of documents that have a lot of text. I can now just go and search in this data set, and whenever I find a sentence that has both bass and play in the same context, I'm going to grab this sentence and I'm going to add it to my training data. Okay, something like this. So I can find things like, for example, we need more good teachers right now. There are only half a dozen who can play the free bass with ease. An electric guitar and bass player stand off on the side, not only blah blah blah. In the same way, if I find these in a document that is not annotated, but I have fish, bass, fisherman, bass, I can just add them directly to my training data and say, I know what is the sense of BASS in this specific thing because I am using the 1 cent per collocation rule. Okay, this is semi-supervised because you can annotate a little, then you can augment your data and train on that, and it works pretty well. All right, now another task that is different, and this is the task that you will see in your homework 4, is that instead of identifying the word senses in a WordNet, you can substitute. Okay, so find a substitute for the target word. This was also a task that was in Semival. You will see all the details in the homework. And what you need to do is, given a word, go to WordNet, find me another word that if I put it instead of this one, if I substitute, the sentence doesn't change its meaning. And I think that is a fun task to play with, and hopefully after when you work on it, you will agree with me. So I'll leave that up to you how you can solve it, and I'll see you in class Friday.